Hi everyone, welcome to my poster titled Motion Discrimination Around the Visual Field. Humans discriminate certain motion directions better than others, and these motion perceptual asymmetries might result from more frequent exposure to specific directions in natural settings. Here we include schematics that represent 3 known direction asymmetries for motion, where the larger arrows indicate better performance. First is the perceptual advantage for cardinal compared to oblique directions. Cardinality in this context includes upwards, downwards, leftwards, and rightwards motion directions. So we classify this cardinal advantage as occurring within an absolute reference frame, since this asymmetry occurs irrespective to where you're looking. But asymmetries also occur for directions within a gaze relative reference frame. For instance, there's a known advantage for directions that are inwards, outwards, and around the gaze position. This we refer to as a new kind of cardinality, which include both radial and tangential motion. Another asymmetry that depends on gaze position is an advantage for radial compared to tangential motion directions. These conditions are a subset of the relative cardinal directions shown in brown. In this study, we test each of these asymmetries at separate polar angles to accomplish 3 goals. First, we determine whether the advantages reported above occur for local motion. This is a test for generalizability, since many studies have used motion stimuli that either span too large an area of the visual field or test too few locations. Second, we measure whether and how the effects of these 3 asymmetries vary at isoeccentric locations. Third, we compare the relative magnitude of each of these 3 asymmetries using the same motion discrimination paradigm, which has not been done previously. We used a 2 AFC task to measure motion discriminability for 8 directions at 8 separate polar angle locations. First, observers learn one of the 8 directions during a practice session, which was then used as a standard direction. On the left, we show an example trial sequence during the experiment. Maintaining fixation, a Gabor target would appear that had a drift direction slightly offset relative to the standard direction. Observers then indicated whether the drift direction was slightly clockwise or counterclockwise relative to the learned standard. Our 8x8 design allowed us to measure performance for 64 unique direction location combinations. Psychometric functions were fit to each of the 64 unique conditions, from which we derived 2 performance measures: sensitivity, which corresponds to the slope of the psychometric curve, which is our primary measure, and bias, which is the magnitude of tilt when the observer is equally likely to respond clockwise or counterclockwise. And this was used as a secondary measure. Better performance would mean high sensitivity and low bias. We fit several linear mixed effects models to the data in a hierarchical manner, with subjects always modeled as a random effect. We did this separately for sensitivity and bias estimates. And for each iteration in this hierarchical method, we add a parameter to account for an additional asymmetry. Accounting for absolute cardinality results in a large improvement to the model fits, as indicated by the large decrease in the BIC score from model 1, which is used as our baseline. But the best model for both sensitivity and bias accounts for either one or both of the asymmetries in the relative reference frame, captured by model 3 and 4. We fit the data in the next section using model 4, since it allows us to compare the estimated effects of each of these 3 asymmetries. Here on the left, we compare model estimates of sensitivity for each asymmetry relative to the global mean. The cardinal advantage in the absolute reference frame has the greatest effect, followed by the relative cardinal advantage and a slight trend of a radial advantage. Here on the right, we plot dots as data points from the observers and lines as model fits, and we do this for each polar angle location separately. This plot in particular shows the cardinal advantage in the absolute reference frame. And this green dot represents the mean sensitivity for upwards, downwards, leftwards, and rightwards motion across all observers at the upper vertical meridian location. In the absolute reference frame, cardinal directions are always better discriminated than oblique directions, irrespective of polar angle. However, the effect is slightly larger along the meridians. This next plot shows the same data points but grouped in terms of relative cardinality. Here, the relative cardinal advantage occurs only at the meridians, where the relative and absolute cardinal advantages combine. The data points at the off-meridian locations are converging, where absolute and relative cardinal advantages are independent at these locations. Additionally, performance is worst when discriminating directions that are oblique in both relative and absolute reference frames, shown by these 4 points along the meridians. In other words, discrimination is greatest for cardinal directions along the meridians, but this is due to a combined directional advantage of cardinality in the absolute and relative reference frames, rather than being due to location per se. The third polar plot shows a slight advantage for discriminating radial compared to tangential motion directions, but this effect does not reach significance. Bias, which is used as a secondary measure, is mostly congruent with the sensitivity measures. There are 2 notable differences from sensitivity, though. Here, the 3 asymmetries have relatively equal weight in the model, and the second notable difference is that the bias measures show a significant radial advantage, reflected as lower bias values for the radial condition. To conclude, the 3 directional asymmetries we tested do occur locally when we test discriminability at separate polar angle locations, but their relative magnitudes differ. Motion discrimination is greatest along the primary meridians, where the advantages of both types of cardinality combine, and we show that this can be understood in terms of directional rather than a meridional advantage. Third, the absolute cardinal advantage accounts for the largest differences in behavior when using a local motion stimulus, as we did in this design. This is consistent with frequent exposure to cardinal motion that corresponds to local cardinal contours in natural scenes. We speculate that advantages in the relative reference frame might become more prominent for global motion, which is in line with its proposed connection to self-motion and optic flow. Thanks so much for coming to my poster, and feel free to get in touch with any questions.